In another video, I went over the ambiguous case and then also how to make the decisions of what it is that you need to find in solving an oblique triangle if you have the ambiguous case. I've given the link to that video in the description of this video if you'd like to go back and see some more examples. Here what I'd like to do is show you an example of an ambiguous case that wasn't presented in that video. So let's recall what we have in terms of the ambiguous case. So first of all, an oblique triangle is a triangle in which there is no right angle in the triangle. And if we have the oblique triangle and the information that we know is side-side angle, then we have what's called the ambiguous case. Now it's called the ambiguous case because there's a lot of different scenarios that might occur, and we have to really look at the information that's given to us, and then also what results as we're working with that information through the law of sines in order to determine what it is that we have, whether we have no triangle, one triangle, or sometimes possibly two different triangles. So let's just look at this thought process to help us determine what we have. Well, first of all, with the ambiguous case being two sides and an angle, that's where you're going to have two small case letters, because those will be the sides, and then one capital letter for the angle. If they follow conventional lettering where your angles are capital letters and then the side opposite that angle is the same letter but small case, in that you will have your two small case letters and a capital letter, and then the capital letter will match one of the two small case letters, and that's when you know you have the side-side angle instead of the side angle side. Now, with the ambiguous case, the very first thing you want to do is look at the angle that they're giving you and ask, do you have an angle whose measure is between 0 and 90 degrees, which would be an acute angle, or do you have an angle whose measure is between 90 degrees and 180 degrees? In that case, you would have an obtuse angle. Once you know what angle you have, if your angle is acute, so let's say we have this right side being not one of the sides that we know, and I'm going to do the angle first and then my sides that I do know. So if my angle is acute, so I'm going to make sure that I make an angle here that is between 0 and 90 degrees. And the side opposite is shorter than the side adjacent. So that's the case I have here where the side opposite is shorter than the side adjacent. Then while I'm solving it, what happens while I'm solving it, if I get an acute angle, so if I actually get an acute angle while I'm solving it, then I'm actually going to get two triangles. I'm going to get the triangle that I originally get, but this angle is fixed, this side is fixed, but there's no information about this angle at the top yet, so that actually could allow that smaller side to swing and actually make a second triangle. And when I make this second triangle, whatever acute angle we have over here, that would be the same acute angle in this spot. So to get the angle that's inside the triangle, I would take 180 degrees from the straight angle, subtract off that acute angle, and then that gives me this obtuse angle. And then I would have to go through the work in solving this second triangle. Now, if when I'm solving it, it's exactly where I get a 90-degree angle, that means this opposite side was exactly the right length to touch the side down here, and you just get one triangle. But if with my acute angle this side opposite is too short and won't make a triangle, then while you're solving it, you're going to get an error in your calculator, and then that means there will be no triangle. Now, if instead of having the side opposite the acute angle being shorter than the side adjacent, let's say you have, again, this side we don't know, but we're going to measure the angle that we know with that, and that's an acute angle. If the side opposite, the yellow one, is longer than the side adjacent, the red one, then you'll just get one triangle. Because if you tried to swing it and make another triangle like we did with the case where we had two triangles, it's over here. It's not giving me a triangle for it. So then I would only get the one original that I would have. So that's the case where the angle's acute, side opposite is longer than the adjacent side, so you just get the one triangle. Now what if your angle is obtuse? So now we're going to take and make this angle greater than 90 degrees, and the side opposite is longer than the adjacent side. So opposite this angle is a yellow one, it's longer than the adjacent side. Then I'm going to get this one triangle, because again, I won't get a triangle if I swing it. There's no other side over here. It doesn't make a triangle, so just that one. If the side that is opposite is shorter than the side that's adjacent and you have your obtuse triangle in there, you're not going to make a triangle. So in that case, you just have no triangle. So I didn't even have to do work with these cases. I could just look at the numbers and compare them. The one that shows itself as you go through the process is when you have an angle that's acute and the side opposite is shorter than the adjacent side. It's while you're solving that you actually get what's going on with the process. Problem where we want to solve the triangle where they're giving me that angle B is 22.6 degrees, side B is 5.55 meters, and side A is 13.8 meters. So to solve the triangle means that I need to find all of the lengths of the sides and all of the measures of the angles. Now looking at this, I have one angle, so the degree measurement of it, and by convention we named it with a capital letter, and I have two sides, small case letters, and I see that it has the length measurements with it. Also, when I have these two sides and an angle, one of the sides letter matches the angle's letter. So that's when I have the side-side angle ambiguous case. Now when we're just trying to visualize this, what we can do to the side, off to the side to just visualize what's going on, is to kind of map it out where we draw just a horizontal line that's not one of the sides we know. It's actually the third side that we don't know. And we're going to think about what the angle is that we do know off of that side. So 22.6 degrees. 22.6 degrees is an acute angle. So I know my angle is acute, so I'm over here. Now that's angle B. Side B is opposite angle B. So going opposite, side B is going to be over here, and that's 5.55 meters. Well, if that's the side that's opposite, then the remaining side that they gave me is my adjacent side, and so I'm going to put that along this run here. So my side A is 13.8 meters. Now look, the side opposite angle B is 5.55 meters. The side adjacent to angle B is 13.8 meters. 5.55 is a smaller number than 13.8. So I'm at this stage where I have my angle is acute and the side opposite is shorter than the side adjacent, so I'm down in here. So I know right now that this is a situation where I have to be really careful with my work and see what I get. Now when we go through and work with this, we're going to start by doing the law of sines. So setting it up with the law of sines, then I know the law of sines is A is to the sine of angle A, as B is to the sine of angle B, as C is to the sine of angle C. And I use the correct proportion from what I have and what I want to know. So I have a side B and an angle B. And I'm trying to find all the other pieces. Right now I have side A, so the angle A would be over here inside the triangle. So this is the angle A that we're trying to find with this information. So then we're going to go, B is to the sine of B as A is to the sine of A. Putting in our values, I have 5.55 is to the sine of 22.6 degrees as, so equals, A I have is 13.8 is to the sine of angle A. Now as I go through and do the product of the means equals the product of the extremes, I have 5.55 times the sine of A is equal to 13.8 times the sine of 22.6 degrees. Divide both sides by 5.55. I have sine of angle A is equal to 13.8 times the sine of 22.6 degrees divided by 5.55. And that's what the sine of A is equal to. So to find angle A, we're going to take the inverse sine of both sides. So A is equal to the inverse sine of that 13.8 times the sine of 22.6 degrees divided by 5.55. Now, when you do that, you're going to get a value for A that's 72.9 degrees. And 72.9 degrees, the way that we round it is looking at the information that we have. If the angle is to the nearest tenth of the one that we're given, then we want to give our angle also to the nearest tenth. And when the angles are to the nearest tenth, our side lengths should be with 3 significant figures. If you need a review of significant figures, I'll also include a link to that video in the description of this one as well. Alright, so that gives me my angle A. Now we're going to go through and we're going to solve this, but I just want to mention where we are with this. We were down this branch, and while solving, I got an acute angle. So if while solving I get an acute angle, there are 2 triangle possibilities with this. So looking at what we had for our situation with the manipulative, I actually got an acute angle over here. So I'm going to solve this triangle first with that information, but then we're going to have to figure what we would get if we were to swing that side over and to get the other triangle. So our first triangle, we have our angle B is 22.6 degrees. Our angle A is 72.9 degrees. And when I take my total of 180 degrees and subtract off the sum of these 2 angles, we are going to get that angle C is equal to 84.5 degrees. So that's our angle C. And then lastly, we want to find the length of side C. So if this is angle B, this is angle A, then our angle C is up here. And side C is the one right there that we want to find. Now we're going to go with the given information that's a full set for our ratio. So we're going to use B is to the sine of B as, now we're going after side C. C is to the sine of angle C. So we have 5.55 is to the sine of 22.6 degrees as C is to the sine of 84.5 degrees. Now again, when we multiply here, because C is in the numerator, we are just going to multiply both sides by the sine of 84.5 degrees to get that C is equal to 5.55 times the sine of 84.5 degrees divided by the sine of 22.6 degrees, and our side C is approximately equal to 14.4 meters. Now that's our first triangle. For our second triangle, so our angle B is still going to be the 22.6 degrees. Our side B is still going to be the 5.55 meters. Our side A is still the 13.8 meters. The values that are going to change a bit to get that second triangle are going to be our angle A, and then our angle C, and then our side C. So angle A for the second triangle, we took that side and we swung it to make the other triangle. So angle A is that straight angle minus the acute angle we got in the first place, in the first triangle. So it's going to be 180 degrees minus the 72.9 degrees. So our angle A here is going to be 107.1 degrees. Now for our angle C. Well, our angle C here, I've got my 22.6 degree angle for my angle B. My new angle A is 107.1 degrees, but I still know that my triangle's measures add up to 180 degrees. So when I take 180 degrees and subtract off the sum of these two angles, I get C is approximately equal to 50.3 degrees. And lastly, we need to find side C. So we're going to do our side B, 5.55, is to the sine of angle B, so is to the sine of 22.6 degrees, as side C is to the sine of angle C, so is to the sine of 50.3 degrees. Multiplying both sides by the sine of 50.3 degrees, we get that side C is equal to 5.55 times the sine of 50.3 degrees divided by the sine of 22.6 degrees. And when you go through and calculate that and then give your value of that side length to three significant figures, you get that C is approximately equal to 11.1 meters. So there's our side C, our angle C, and our angle A for the second triangle. So there's an example of a situation where you had the ambiguous case and you had an angle that was acute, the side opposite the angle was shorter than the side adjacent, and while I was solving it, I got an acute angle, so then I knew that I had two triangles.